So yeah, welcome. Thank you for the introduction, Stefan. I'm really happy to be here today as a speaker. I've been here today before as a listener, and saw a really interesting presentation as well. My name is Philipp Zimmermann, and as Stefan said, I'm a CEO and co-founder of Franca Imica. What we do in particular, I will tell you a bit later, and also you see, of course, a demonstration running here. But I want to tell you a bit of story about robotics in general, where robotics coming from and where it's going to, or at least from our point of view. And to give the big picture, I always like to introduce with this slide a similar slide probably you have seen already before in different presentations, but mankind, we have already always described the times in our history through the tools that we've been using, starting at the Stone Age, where we used the stone pick to enhance and to be more powerful and creative, and so on and so forth, going through the different industrial revolutions. And we strongly believe that we've already entered the age of robotics, and the message carrying that, meaning the robot, seeing the robot as a tool to enhance us and to support us, rather than to replace us or to be dangerous. So we see the robot as a multi-power tool, so to speak, that we can use to be more powerful, to create things, to create art, tools, and so on and so forth. So with that being said, just a brief summary, maybe what I'm going to talk about. So I'll show you a little bit where robotics is coming from, what has been happening over the last years. Robots have been around for roughly 20 years, even though maybe a lot of people don't really, or we haven't really seen them around because they're hidden behind safety cages and in big factories. What robots are today, where it's basically going towards tomorrow, so short-term view in the future, and then long-term what our goals are and where we think robots are going to in the future. So in the past, really 20 years, robots have been around, but what have they been up to? So mainly they've been welding tasks, or painting, or lifting heavy cars, stuff like that, mostly in automotive, where robots have been around, but that's basically it. So a picture like this is what you typically see when you look into an automotive factory. There's lots of robots, there's safety fences, there's no humans in the areas where the robots work, and that's it. The reason why that is because they're dangerous, of course. They will hurt you when you come close, so you need to protect ourselves from them. And the tasks are very limited, so even though we think our automobiles are mostly manufactured by robots, that's not true. Only maybe 20–30% of the tasks in automotive are automated via robots. The rest is still manual labor. But these are the pictures that we see. Robots are dangerous, right? So those are the reasons why we need a safety fences, because even if we put a sensor to the industrial robot, there's no chance of survival, or at least of no pain. So for a long time, everybody in the world agreed to robots are dangerous, period. There was no research behind that underlying that statement. It was just a fact. Basically, until one day, a young professor in Germany stood up and said, well, you're all wrong. Robots can be safe, and I'm going to prove it to you. And he started research in this kind of area, and we see here now early videos from roughly 15 years ago, where you see a robot moving quite fast, but as soon as he reacts, detects a reaction, a collision, he reacts and becomes compliant and soft. In these videos, you can imagine they made it around the world. The whole research community screamed and said, well, how can you do this? This is dangerous, but it worked. And it got quite a lot of fame. But people started understanding, okay, wait, maybe there's actually a way. Maybe robots and humans can actually work together. Maybe robots aren't dangerous per se. So all the companies started developing. What we see, classical industrial robots, those are the robots behind safety cages. They lift heavy stuff, they do the task as mentioned. But basically every major robot manufacturer started developing different kind of robotics, lightweight robotics or collaborative robots, cobots are they often called, meaning robots that potentially can work next to a human. That of course brings a lot of advantages when you don't need these expensive safety cages, and of course logistics are way easier when you can work next to a robot like a human coworker without a safety fence. So, you know, these are some of the major manufacturers. Maybe Universal is to be highlighted as the most sold cobot. I think they've sold over 10,000 robots so far. Out of, you know, that's quite a lot from one robot only. This is an American producer. Rethink Robotics, also quite successful. So they started solving the problem of safety, meaning once it collides with a human, it will stop, right? So it protects you as a human, you can work next to it, and you're safe. However, that's not the answer for all the problems. If we look at robots today that we can maybe have at home or we can buy for homes, those are the robots that we typically see, or that's how they look like, right? So they can tell you how you feel, or what you want to do, how the weather is tomorrow, or they, you know, can vacuum. They can, I don't really know what Pepper does, but it can wave and show you the way to the bathroom, or can deliver things to your hotel room. But you know, what do they all have in common? They have no arms. This robot has arms, but they're not really doing anything, right? They can't give you a bottle of water. They can just show you or wave to you. And even this robot, it's a really, really nice robot. It's operational in a lot of hotels, so it will bring you, you know, your room service basically. But the problem is, it can't even push the elevator button. So most hotels have elevators, so it needs to be integrated via software, which of course is expensive, and not, you know, not all elevators are as modern that you can do that. It would be much easier to give it an arm to press the elevator button, but apparently that's not so simple. Oh yeah. However, all the forecasts say big numbers, especially in collaborative robot market, right? So looking at the numbers here, of course, 2015, most of the robots being sold in automotive, but going over the next 10 years, automotive is, you know, relatively small to all the other industries that there are. And that makes sense because all the other industries are quite big. Electronics industries, much bigger than automotive. Hardly automated yet, but people think, oh, once I have, you know, safe robots, I can sell many more robots. But why hasn't that happened yet, right? So safe robots have been around for 10 years as well, 5 to 10 years, but these numbers haven't been reached yet. So what is holding robots back today? And those are basically the reasons. So besides being safe, which is obviously, you know, necessary, most and for all, but robots are expensive. So especially for smaller companies, you really need to think hard whether you can afford a robot. They're hardly usable, so people can't work alongside the robot. People working in the factory, they don't know how to function the robot working next to it. So you need to train or hire new personnel for your companies. You can't scale because robot programming is the most complicated programming of it all. You program a robot, it takes weeks and months, and it's one robot cell. So if you want to have a second robot cell doing exactly the same thing, basically you have to start all over from the beginning and can't copy paste, which makes it of course a big hazard, and you can't scale it. But most and for all, the lack of sensitivity that robots have limits the functionality. So as we saw in the beginning, they do welding, painting, all these things. They don't require a sense of touch because all these robots are missing one thing, That's lack of sensitivity, the sense of touch. That's what makes us so powerful. That's why I can hold these things, or I can drink a bottle of water while still looking at you, because I can feel. And that's a big, big important thing to understand in robotics, because for us humans it's so self-understood and so easy that we have our sense of touch, right? We have 5 senses, or some people argue more, but sense of touch is the most important of them, which we often don't think. We always rely on our eyes, but without our eyes we still would be fine. There are a lot of people actually are with no vision, but they can still live in the world. However, without a sense of touch, you wouldn't be able to open a bottle of water, or to close a bottle of water, or open a door. The best comparison that I can always give is probably most of you have been to the dentist and had your half jaw kind of numb after the injection. And so then a few hours after the dentist, you can technically chew. Your jaw is still functioning. You can close it and you can open it. But when doing so, you don't know if you chew the potato, the piece of meat, or your own tongue. So basically you don't chew until you get your feeling back. And that's what enables you to chew. Not the apparatus going up and down, but actually the sense of touch, knowing what you're doing. And that is what robots are. Even when they're safe, that's what robots are. They have no sense of touch. They don't know what they're doing. And that prevents them from interacting with the real physical world. That's why they can't push a button. They can't insert something. They can't do anything other than position-controlled automation. And that's where we come into play. So, as Stefan said, our background is in the German Aerospace Center, which is basically the German NASA. Over the last 40 years almost, the research has been done on easy programming and on soft robotics, so on robots, giving robots a sense of touch. That happened in the German Aerospace Center because the original idea was and is to keep astronauts safe, right? We have astronauts flying in space, and for every little task they need to leave the space station to push a button outside on the spaceship or enter a relay or anything. That's always, potentially very dangerous. Why can't a robot simply push a button? Well, for exactly that reason. You can tell him to do so, but you have no feedback. You don't know what's happening. Is it pushed or not? Is it pushed too hard, too soft? Did it hit or not? We don't know. So that's the reason why they started working on a sense of feedback like we humans have. So we have our ligaments. Robots don't have that. But the solution that people came up with is torque sensing. So also what our robot has here, in each joint, each of the 7 joints is a torque sensor, measuring the torque in each joint, and therefore knowing the real force that's applying. So we have when you have a direct model of the robot, you can compare the forces that you expected to the forces that are actually happening, and then you can technically calculate the external forces that are applying to your robot. And that is similar to what we basically have, inbuilt, and because it's highly integrated, it means the reaction time is really, really fast. Right? We have, as humans, automatic reactions. As soon as I hit something, I can grasp it, or I can retract, and all this electronics basically are already in the joint itself, giving the robot a really fast reaction, making it safe enough to be around humans. Basically, the requirement is you need to react faster than a human. We have 50 milliseconds-ish reaction time, meaning in this 50 milliseconds, I'm at harm because I can't protect myself. After 50 milliseconds, I'm fine because I can react. Until then, the robot needs to protect me. So what we came up with is our robot Franca. Franca is a 7 degree of freedom robot, very similar workspace to what we have as a human arm, and it's as sensitive as it can be. So I will demonstrate it, and I'll also invite you later to come in the front and feel yourself to see how sensitive it is. The other big problem I said is programming. So how can we solve that? Our approach was app-based programming. Anyone, you know, can click a few apps together like we do in our smartphones and program a robot. And all this behavior allows it to actually do assembly tasks. So the story being here told in the video is actually the engineer programming two robots to build itself. Okay, I'll wait. Is this better? So the story here is that the engineer programs two robots to build itself, right? To assemble itself. And that's actually not a marketing gag, that's actually our own production. So our production is in Germany. We're a German-based company. And the production looks like that, robots assembling robots, right? It would be a joke if we wouldn't do it because, you know, we claim that's the first robot to do assembly. So why wouldn't we use it in our own assembly lines? And the next thing is scalability, right? So programming one robot is fine, but you know, you want to program hundreds and thousands of robots, maybe doing the same or similar tasks. So our robot is connected to the cloud. You program one robot and you can distribute it to as many robots as you want, no matter where they are in the world. And you instantaneously have the exact same robot program and thus the exact same quality of production, no matter where you are. Additionally, of course, you have all the data in the cloud as well. So in total, you have a robot that is easy to program, flexible, and reprogrammable. It has an agile workspace like a human arm, and it's connected to the cloud. So you can set it up within minutes rather than months, and you can program, you know, 1,000 robots at a time, no matter where they are in the world. And being in the cloud, obviously you have all the data in the cloud. You can, you know, put any additional intelligence like artificial intelligence on top of it, right? So you can let them learn from each other. You can do predictive maintenance. You can make them optimize each other, all these things. Maybe the best modern analogy that we could come up with is the development we had in computers, right? The big old machines, then eventually we had the PC, and now we have the iPhone. Everyone has like a high-end computer in their pockets, or a smartphone, I should say. So that's what happened to the robots. You know, the first robot, then the classical industrial robots, now having really soft and sensitive, intelligent robots. And the programming, you know, from having these Lochkarten, I don't know what the English word is, punch cards, right? To, you know, better, easier programming, to really app-based programming we have nowadays. So robot programming hasn't really changed. So this is actually still how you program robots nowadays. Well, this is how you will program in the future. And this, of course, opens up whole new industries and use cases. So from being very limited, mostly automotive, doing welding, painting, all these things, you can imagine it opens up to basically anything in industry, but also at home, right? So, of course, electronic markets, one of the biggest market, or maybe the biggest market in the world, hardly automized. That's why it's all pushed to low labor countries. With low manual labor costs. Well, these can be automated now. Small and big companies can automate. It doesn't really matter. And the idea is, and what makes it really powerful is that we're just giving it as a platform technology. So I use the smartphone as an example as well here because I said it's app-based programming, while we open up the platform and invite everybody to contribute and write own apps, right? You can write your own apps, push them to our app store, and distribute them through the app store, making the ecosystem more powerful and enabling such more and more people to use robots, right? Not only big companies, but also small companies, and even, you know, private people at home. So think about the possibilities of that. Brings me to my favorite slides of all. I'm German, and I love bread. We love our bread. And you know, when I was young, we would go to the bakery store on the weekends, and there would be fresh baked bread, and it would smell good, and you know, you could choose what smells the best and what looks the best. And that has kind of vanished. So over the last 10, 20 years, more and more bakery chains have popped up everywhere. You can buy your bread at the gas station, and it's not the same. So these, of course, these huge chains, they pre-bake their bread in the manufacturing sites, which is of course highly automated. They ship them out to the vendors and sell them in the morning. And that is ridiculous, because so where I live in Munich, next to my flat, there's a bakery chain, of course, and the bread tastes so bad. It makes me angry every weekend. And it's not even funny. I hope nobody from that bakery, or maybe I hope somebody from the bakery store would be here, because it's really ridiculous what they sell. It has nothing to do with, you know, classical German bread, but of course it's cost effective. And sometimes, you know, I drive 30 minutes around the city to go to a small individual bakery to buy real bread. But so what's happening? Of course, the bakers, the individual baker, they can't compete, right? First of all, they don't find the people to get up at 2 a.m. in the morning to bake all the bread, and they can't compete cost-wise against all these, you know, mass production automations. But what if the individual baker can buy a robot for a low price, $10,000, $15,000, buy the bread baking app that maybe someone here in the Silicon Valley wrote, a little startup, and he can automate his own production for the same costs than the big bakery chains, right? So that's actually my dream, why I'm doing all this, to reshore bakery. You know? And I mean, the good thing is that already a lot of startups kind of following this way as well. So there's one startup here in the valley called Nourish. They want to be, you know, the biggest fast food supplier, but there's also Cafe X, for example, in San Francisco, doing robotic cafe. So companies realize that the need is there. So Nourish, they want to do fresh baked food out of the box. You know, order it via app. But what they are missing is the platform technology, right? A technology that is cost-effective, affordable, and easy programmable, and actually capable of, you know, doing what is needed to be done. So this is just one example out of many, maybe not the most technical example, but my favorite example. That's why I keep bringing it up. And with that in mind, I mean, imagine where it's going. So of course, the industrial version is the first version that we bring into market. And that's where robots already are and coming more and more. But we want robots in our homes. Right? You can buy robots for your homes. They're just very, you know, not capable of a lot of things. But imagine what could be possible if you have actually a robot with an arm that can actually give you the glass of water, that can put the dishes into the dishwasher for you, or fold the laundry for you while you play badminton in the garden. So all these things are possible, and I want to give you a short outlook into the future of what I believe the future looks like. And this is a project that we're working on, and that's where actually our heart is. So in the south of Germany, south of Munich as well, there's a city called Garmisch. It's a very pretty, magical little place, very old population. And a few years back, there was a very wealthy industrial couple, and they passed away, and they gave quite a lot of money to this little city with the goal of making life better for the growing elderly population. And we luckily we got funds for a project that we're doing there now, which I want to introduce you to in the next slide, but I think I have to do it manually. It's in Bavaria after all. So Gummy basically being a mobile robot with 2 arms on the side, just a bit smaller than these. As I said, so test homes are actually now being built for elderly people to live, or all the people to live there, together with the robot, and the goal is to enable them to live by themselves independently longer. If you have someone at home, basically 24/7, where any doctor could log in, use it as an avatar, help you with a simple task. So it's of course far away from the iRobot that we know from the movies, but step by step it's going there, right? Putting your shoes on, opening the doors, all these things. So this is just a short outlook from our point of view, but you can imagine, so of course there's many more robots like this coming, so the technology is going to be more and more available. So I think it's a really exciting time to be able to experience in it. The next 10, 15, 20 years are going to be a big change in robotics and such in our lives. So with that, I think I want to finish, and I guess we have a short interview as well, or a discussion. If you have any questions, I want to give you a short demonstration as well on the robot first, maybe. But afterwards, if you have a few minutes, please don't be shy. Come to the front so you can see better and actually touch and maybe program a robot for yourself, because probably most of you have never programmed a robot, I assume. Well, today is your chance. It's not that complicated. And as you can see, the robot has been working and doing its work in the background. But anytime I can just interact and stop it or let it continue. Right? I can go, something is wrong, I can change something and let it continue. And actually the tasks that you see, I hope you can kind of see what it's doing. So it's pushing these blocks to the end, picking it up and stacking it. So that seems like a rather simple task. It's basically a pick and place task. Pick and place tasks have been automated for many, many years all around the world. But the big difference is, up until today, if you want to automate pick and place, you can only do it via precision. So you need to make sure that whatever you want to pick and place is exactly at the same position. I mean 0.1 millimeter or even more exact at the exact same position. If it's not, it's going to be an error and it's going to be interruption. The robot is going to stand still. An expert needs to come and, type some lines of codes or whatever in order to get it running, because of course the coworker, he can't do it or she can't do it. And to guarantee that the workpiece is always at the exact same position also is not so easy. It's actually quite difficult and thus quite expensive. Here, however, as you see, it's just pushing it to the end. Well, now it's not because there's none. Until it feels it reached the end, and therefore guaranteeing, I know roughly where it is, and the rest I can feel and grasp it and place it here. And also here, it pushes these, stacks these blocks on top, not knowing how many they are. So it just goes until it reaches the bottom, feeling the bottom and putting it. Meaning it can differentiate between a collision and interaction. So it knows it's not a collision and I need to stop, something dangerous has happened. It knows, okay, I'm awaiting, somewhere to feel something. Okay, there it is. I can stack it. That's how we would do it without eyes, right? I can, see, the robot does it even better. But you get the idea. So that allows you to automate things that are possible today already, but much easier and much cheaper, much more cost-effective, because you don't need the precision in feeding anymore, for example. Another, how do we let's turn this on? I should know. Actually, what we could do? We could put this on the screen. Can we?
Yep.
So here you see actually, can you make it full screen? So here you actually see how the robot is being programmed. It's a browser-based program, and you see basically on the bottom right you have different skills or tasks that apps that you have on your robot installed, like move or pick or insert. On the left you have programmed tasks already, which is a combination of different skills, and on the top you just click them together as you'd imagine to do. So you can rearrange them anytime like this. So to give you maybe a demonstration of how sensitive it is. So now it's just moving around, and maybe I'm just standing here and I collide. And you saw maybe it wasn't a hard collision, right? It was very soft. I can say maybe something is wrong, okay, and I give it a little push and it will continue. So I'd gladly invite you afterwards to come and to feel yourself, because literally a little finger is enough to do so. And of course, this makes the robot safe. But the big difference is, because there is, of course, a few collaborative robots already out there, but being collaborative, so being able to stop when you collide, doesn't make you capable of doing real interaction and real assembly. So what you see here, for example, right now, is the robot is not moving, right? And I can try to move it a little bit, but it's very stiff, very strong. The brakes, however, they are open. The motors are running. It's just a software telling the robot, flex your muscles, be very stiff, right? Like this. But as soon as I give it a push, it's very compliant. And it lets it move like a fabric. It weighs around 18 kilograms, but also I invite you to do this yourself. You won't feel it. It feels like there's no weight at all, because it compensates its own weight. And as soon as it feels that I want to go into a certain direction, it supports me. So it activates the motors in this way to go there. Basically, what your car does when you do your servo drive, this is just over 7 dimensions, not just over 1. So a good way to see it is, for example, right now, I'm only allowing it to rotate around this point. So if I want to teach it now, it will only go there. So everything else is kind of blocked, right? So it's like flexing, not allowing me to go there. Just in this rotation, I can do it. So all this is software, and this is what enables it to actually do this manipulation task. This is how we get a key into a lock, right? We don't need our eyes, to identify the lock. But what then? We have a strategy. We kind of feel we're strong, force in one direction, compliant, but very strong in the other direction, and that's how we get to do it. And it's very complicated. A good example to understand how difficult that is also if we look at ourselves as humans or as children. I mean, for those of you who have children or have seen children growing up, when they come to, when they're born, we are complete. We have everything. We have muscles, we have nerves, we have everything. We can see rather quickly, we can taste, we can hear after a few weeks, but until we have these machines under control, it takes years, 10, 15 years easily. After a few months, we can compensate our own weight, we can actually hold our own head eventually, but give a 1-year-old a key, it will never be able to put the key into the lock. Why not? Because it's so difficult. It needs a strategy, and it will learn that over years and years and years and years until it really is in control of it. And that's basically what the robot can do, right? We can tell him how stiff, how strong, how compliant to be, and with the right strategies, that's allowing the robot to actually doing quite complex tasks. For example, this, maybe Lucas, you want to program this for me while I explain. So this is just a box with different connectors. And we're using, I think, the HDMI connector, right? So inserting a connector is something, or a key or a connector is something impossible for a robot nowadays, because unless you're 100% precise, you can never get the connector in. We all know the struggle with the USB, right? No matter how, it's always not going in. And how do you do it? You don't use your eyes, you just, because we know the USB, right? We can actually check before, but we don't. It's easier just to feel, right? So it's a really, really good example. And of course, in the real world, we can never be 100% precise. And even with this setup, it's a very, very prototypical setup, just, put in here. It can never be precise. So it shouldn't be able to insert this unless it has a sense of touch and the right strategy to kind of wiggle it in there. And of course, that would take weeks and months to program unless you have an app for it. So as you can see, he's actually programmed on stage live now. So the app asks Lucas to give him some positions that it needs to know, because actually it doesn't have a camera at this moment, or it's not using its camera. And also what you see, there is no teach pendant. So all that Lucas is using is the pilot on top. You can either program the software directly through the computer or the iPhone or whatever it's using, or control the software through the pilot, enabling it once it's programmed to keep both hands on the robot at all time. Are you done already? Oh yeah, done already. So that was fast. And I'm not sure how well you can see from afar. Right? So now we just programmed live on stage what usually would take you a month, even having the technology of the robot. But so you can understand the leap or the big gap in technology. This means millions of people do this every day in the factories because you can't automate it today, not in a robust way. So maybe this gives a good understanding of what's possible and what's coming. And of course, with the platform being open for people to participate, there's actually no boundaries, and I hope it will go into any different kind of field. So I guess that's for it. That's it for now. Please come to the front and don't take my word for it. Thank you. Yes.
So it looks like you have a pretty straightforward programming interface for you using the robot arm as it is in place. But say if you're a system developer for integrating this into a larger application, say like a mobile robot that you want to use this particular arm on, what type of application interfaces are available for that? Say, for example, I have a mobile application that says, okay, go down the hall to the refrigerator to pick out a beer or what have you, that wants to exchange data between the robot arm and the mobile platform, for example. Do you have facilities in place for that type of development, or is it more like what do you have for that?
Yeah, so what's important to understand is that the software is service-oriented. So for the software core running on the controller, the robot itself is just a service. The gripper is a service. The conveyor belt or the whatever you name it is a service. So once you have an interface, you can use whatever and integrate it into any system and let it speak to any system what you want. So for this, of course, you need to connect quite a few different technologies, but yeah.
Fred?
So you talked about portability of these programs. So taking as an example the plugin that you just did,
right?
If you were to then port that to another robot,
yeah.
How close do the two pieces need to be in order to make the program successful? I mean, what kind of adjustment would need to be made on each one?
So let's say we program this here and we copy it to the cloud, and somewhere in South Africa in the factory the task is supposed to be done, right? That's your question. So of course you never know if the layout is exactly the same, but that's no problem because the way it's programmed is so easy that you can reprogram or actually reparameterize quite quickly. So either you make sure that it's rather the same, or once it's programmed, you go there and quickly reparameterize. Say, okay, maybe the connector is a bit different here, and you can quickly adapt it. But the difference to now is, right, you would have to program it here, it would take you a long time, and then you would have to fly over to South Africa, which you probably wouldn't do, but someone else would do it in South Africa, program the whole thing, and you have a totally different program, of course, in the end.
Any more questions?
I just wonder, since like your robot is trying to pick a spot at a random place, like for example, there is a wood block in the wall frame at any position, there should be tons or thousands of the solution for the robot to reach it,
yes.
Right? Since it has 7 joints. So I just wonder how your robot figure out the route to reach it. Is it there is some method for it to reach it?
So that's a good point. Because of 7 degrees, yes. makes the math behind it quite ugly, and I wouldn't be able to explain it here on stage. However, so there's certain tricks to be used. So it basically depends on the app, but what we use mostly is, because often you have use cases like this where you have things on the table and you work on a tabletop, or you have somewhere an area where you can move freely. So saying, maybe the robot's supposed to do something here and then something here, and the app will ask you for a position above in a plane where it can move without any hazard. So in there we'll just move as fast as possible to the next position and then do the tasks there. However, if there's anything in the way, you need to either let it know that's in the way, or you use, of course, vision systems. So for example, we have an external camera that's not part of the robot that we just integrated, just glued on or screwed on here. And then you can enable, of course, pathfinding or all these kind of different technologies. But simplest way is just to make sure that there's some area, some plane where it can move freely without any collision, and then go to the next task. But still, you need the math to let the joint work its way and know basically the inverse kinematics to understand how to move, how to get there. Yeah.
To anybody else?
Can you comment on public robotics education programs like First Robotics Competition, and what percentage of the people that apply for jobs with you have that experience?
So people applying for jobs with us, so since we're based in Munich, we're roughly 95 employees in Munich. Most people come from university, from different universities in Germany, but also globally, coming out of robotics programs. So, because this technology is so different from what industrial robots, it has nothing to do with each other, meaning that classical industrial robot engineers, they're not really the right fit necessarily for us. So actually the young professor that you saw earlier with a knife stabbing himself, so he's a professor in Munich, and a lot of our employees going through his school, for example, and then coming to us. First Robotics is a program that I've only learned about being here, and we want to engage with heavily. We do engage with universities in Munich and with schools, because I think it's a technology like a smartphone, like a computer that we need and our children need to grow up with. So we want to get the robots into schools and universities to make it really self-understanding for them. As we already see today, when we have some universities already using these robots, the tasks that the students do are unimaginable. Even we can't imagine. But when we go to companies and have a robot there, and then we come back a month later, they program something in a very classical old way because they're so bound in their way of thinking. And that's actually a big challenge for us to make people understand how to leverage the technology in the right way. Not to use it as an industrial classical robot, but the solution, pushing it maybe into the corner of the box and then picking it rather than using a camera, because it's way more reliable and robust, right? For a student, that's absolutely clear, and he will just do it. But for the engineer who's been working there for 30 years, he knows, oh, I need a vision system for this, because... So those things are quite difficult for us to bring across, to make people really understand the different way of thinking.
Thank you. So, and I was actually visiting Frank and Mika in San Francisco, and kind of did also a little bit about the moving around.
Because this one so in the back is the panic button. Oh, so if you push it too hard, no, you need to push it, but there's two ways of pushing it.
Okay, here we go. So I invite you to come out and try it yourself, and then also kind of see how the programming works. And thanks again. Great. Thank you.
Thank you. Yeah, please come, and if you want to program some pick and place or see a reprogram or do some collisions.